Okay, so good afternoon. Okay, so a very good afternoon to those who came. Welcome to the 17th edition of our online webinar series. Today we are very glad to have Mr. Krishanu Sarkar, who is currently in the third semester of our IACS BSMS UG program, who is aspiring to take a major in physics, and who is also currently working in the group of Professor Arnav Das. He is a professor in the School of Physical Sciences, ICS Kolkata. Krishanu is a dedicated learner of physics, and I've always seen him very keen with the subject. And if you can always spot him in the front desk of the library, reading various stuffs, writing on something, discussing notes, and he's also very enthusiastic to interact with people from various backgrounds. Currently, he's focusing on some topics in quantum mechanics specifically, and that's all what he will be going to tell us. So, just a few short remarks. As an organizer, I'm telling to the people who are new to our webinar series, we are starting from 7:30. The whole webinar will be recorded and uploaded in our YouTube channel. So keep in mind this fact while you ask questions. You can, of course, ask questions in the chat when the speaker speaks, and that can be answered by the speaker later when the talk ends. Or the best will be if you ask your questions later at the end of the talk. You're free to ask them. And the talk will comprise of 40 minutes or 45 minutes of lecture with 5 minutes of questions, or it can get longer with supplementary discussions and so on. So, with that, I would like to hand over the stage to Krishanu to take over. Krishanu, you can just share your screen and begin your talk. So, over to you.
Yeah, sure. So, hello everyone. Uh, so, what I'm basically going to talk about today is it's a pretty basic stuff known as free particle in quantum mechanics. So, uh, am I audible and visible?
Yes, Krishanu.
Yeah. Okay. And the screen is shared, right? Okay. So, we are going to start with something called quantum free particle. So what basically a quantum free particle is. So the classic definition says that a free particle is some particle which in some sense is not bound by any external interactions or which you call external force, or equivalently it is in a region where the potential energy doesn't vary. So in classical physics, this basically means the presence of a field-free space. I mean, a particle present in a field-free space. And in quantum mechanics, it says that some particle is in a uniform potential region where there is no change in potential, that is with space del v del x is equals 0. Also with time you can consider. So the Schrodinger equation for the free particle in one dimension is basically this. I'm writing the time dependent one. And what happens is basically the potential term is clearly time independent in this case because it's simply 0 I have put. So, so ultimately, which results in separation of space part and time part solutions in this. And so if we write the space part Schrodinger equation, it seems like this, and the solution to which, I mean, if you write the general solution, it is given by the superposition of these two basically plane waves uh, traveling in opposite directions, and then a and b are some integration constants with the k parameter as square root of 2 me by h bar, where e is the basically the energy of the free particle. So now there occurs a problem that if you consider any of these components and try to normalize it, you will find that it is not normalizable because I mean the integral is blowing up to infinity. So basically the integration doesn't converge at all. So there is no normalization there. So the solutions obtained cannot be normalized. So as we know that the bond interpretation, the probability interpretation mod chi square gives you the probability only when that integral basically converts or the integral is finite. But in this case, what you see is the integral is blowing up. So you cannot normalize that wave function. So how do we interpret it at all? So basically, any particle or free particle, then it's a problem with, I mean, any kind of particle or specifically this free particle, as you can see, there, if you try to solve the Schrodinger equation, you will arise at this kind of point where you cannot normalize the solutions very frequently. So how do we deal with it in quantum mechanics? So my focus is to establish some sort of localization, because in classical notion, as you can say, a particle is basically something which has a definite position at first. So what I want is a definite localization. So what I'm going to do is, I mean, this is my basic idea, that if the wave function corresponding to a particle is somehow made to vanish everywhere except the neighborhood of the particle, then we can have some sort of position space localization and we can establish some notion of particle. So how do we basically implement this kind of things? So the way is to consider a wave packet. Uh, so what is a wave packet? Uh, so any wave packet you can say, I mean, the characterizations of the wave packet are given by it has to have first of all a localized wave function which we want, and then it consists of a group of waves of slightly different wavelengths with phases and amplitude such that they interfere in a I mean they have to interfere constructively in a small region, and then elsewhere they will interfere destructively, so you get a localization. So now we talk about how to construct such a wave packet. So wave packets can easily be constructed by superposing many plane waves of different wavelengths and different phases and amplitudes, of course, such that you get those constructive interference in a region and destructive elsewhere. This is done by means of Fourier transform. Uh, so this is basically animation which shows the a wave packet there. Those blue ones are basically representing your plane waves, and those plane waves are superposing to give you this sort of wave packet. Now, how do we write the wave function of a wave packet? First of all, so basically what happens is, back then when we tried to solve the Schrodinger equation, we got the form a e to the power ikx and b e to the power ikx. If one considers those a and b terms as amplitude terms, and here the basic idea is we take many such waves and superpose them, because all of them are solution of the Schrodinger equation. So we can do that because the Schrodinger equation is a linear equation, of course. So the linear superposition of the solutions will also be a solution to the equation. So what we do is we consider that amplitude to be a function of k. That k is square root of 2 me by h bar, which I have already established before. So the form of the position space wave function in that case is given by this 1 by square root 2 pi and this definite integral, where e to the ikx part is basically the space part solution, and that omega t part comes from the time part solution of the Schrodinger equation. And then phi k is basically the amplitude function. Phi k, I mean, later we will see that phi k actually determines the various behaviors of the wave packet. And as you can see clearly that if I place t equal to 0 there, then the expression you get for initial wave function, that is psi x0, that's basically, clearly you can see that that's basically the Planck-Russell's theorem, right? So basically phi k and psi x0 are connected by a Fourier transform, you can clearly see. Now phi k, I mean, just by inverse Fourier transform, you can write phi k in terms of psi x0 like that, 1 by root 2 pi and then that same integral. So Now we come to talk about something special known as Gaussian wave packet. So what is really Gaussian wave packet? So the wave packets whose initial position space wave function, or basically amplitude function, which I am talking about phi k, is Gaussian, is known as Gaussian wave packet. So if we want to see an example, then this can be a good one. Phi k equals a exponential this, I mean k minus k0 square, and c has to be negative for Gaussian wave packets, otherwise it won't be Gaussian. So where a is some sort of normalization constant and c is some sort of constant. This is a form of Gaussian function. So let us talk about why are we interested in this kind of special wave packets. So the amplitude function being Gaussian carries some very good consequences, which are basically the Fourier transform of a Gaussian function is also Gaussian indeed. So the amplitude function being Gaussian ensures that the initial position space wave function was also Gaussian. And then you have this property of Gaussian function that it has a finite width, which is basically the standard deviation of the Gaussian, which takes significant value within the width and then vanishes rapidly. And after the standard deviation is crossed, then Gaussian very rapidly vanishes, as we all know. So using this, we can produce some very good sort of, localization realization basically. And this another thing is that in combination, this amplitude function being Gaussian localizes both position and momentum, because as we know that to get to position space wave function to momentum space wave function, you need a Fourier transform. And if it is a Gaussian, then its Fourier transform is also a Gaussian. So if you localize here, I mean, that should be, of course, that should be within range. I mean, not that every time you will get some localization, but for some special conditions, you can simultaneously localize this position and momentum up to some precision. And of course, the widths of the two Gaussian, if you connect them by Fourier transform, has some unique dependence on their product of widths. So that actually produces some sort of realization of Heisenberg's uncertainty principle. And this is some sort of just a typical Gaussian function e to the minus x square, which, as you can see, very rapidly diminishes with increase and decrease in x about 0. Now we talk about time evolution of a wave packet. So we are all we are interested is basically the time evolution of a Gaussian wave packet in a force-free media. So there is no such external interaction affecting the dynamics of the wave packet. Now, as a result, the potential energy term always remains independent of time for any wave packet in such a media. So this allows us to separate the space part and time part solutions, and then basically, and for this reason, what you can do is you can write the wave function at any time as this, and where ikx part comes from the space part, and then that omega k t dk that part comes from your time part solution. So this is a propagation. I'm showing you the propagation of some sort of Gaussian wave packet in a complex plane. This is how it propagates. We will see the expressions corresponding to this I have calculated later. Uh, so before that this thing here, this omega k, that omega k terms basically corresponds to ek by h, where ek is the total energy, which depends on, of course, that k term. So now this function, basically this omega k function is known as the dispersion relation for the wave packet. So if we consider a general position space wave function, basically which takes its peak at k equals k0 and we Taylor expand it, then the expression comes something like this. So something like this. So usually there are two kinds of approximation which are done. I am saying you about treatment of a general wave packet, not specifically a Gaussian wave packet. I'll show you for Gaussian wave packet too. So the dispersion relation for this sort of free particles which we are considering, that is basically given by omega k equals h bar k square by 2m. So as you can see in this expansion, if you plug in the omega k, then you can see that after second order all those terms will be zero. So there is no significance of the higher order terms after second order in which we are considered about. So when do you do this kind of, I mean, two types of approximations are there which are done usually, the linear ones and the quadratic ones. So when the linear ones are done, the linear ones are done basically when this second term in the expansion is very, very less than one. In that case, you can ignore that term and just simply write the remaining and then try to evaluate the wave function. So the result I got is basically the position space wave function. An initial position space wave function comes out to be something like this, and then which ultimately results in a probability density of uh, this at any time t. So as you can see that under linear approximation, this psi mod psi x t square is basically equal to mod psi x minus d omega k dk at k equals k0 times t. So it clearly says that the wave packet is basically some sort of moving in a, I mean, with a constant velocity, which is d omega k dk at k equals k0. And k0 is where basically that function is speaking. So, I mean, in this case, what happens is the wave packet propagates undistorted. So what is basically undistorted? Undistorted basically implies that the shape of the wave packet doesn't changes with time. It remains intact. So under linear approximation, the results are somewhat like this. And now we go to the quadratic approximation. So in this quadratic approximation, you have this second term included too, and the higher order terms basically vanish. So the position space wave function in this case is given by something like this: I xt equals this, where this hxt is this is getting bigger. So this hxt term is somewhat like this. This is a huge term, I know. So, but then knowing the function fk minus k0, which basically is the representation of this phi k only, the amplitude function, allows you to work with any kind of wave packet you want. That amplitude function you can choose by yourself and then try to evaluate what will be the corresponding wave function, and then probability densities, etc., etc. Under quadratic approximation in general, you will see that the width or spread of the probability density function, which is basically Gaussian, changes with time. This event is basically known as distortion. So there are several factors on which those distortions happen, and I'll take on them later. So this is basically animation showing you how a wave packet propagates with distortion. This is the plot of the basically the real part of the wave function, which basically changes with time. Now we go towards free particle. Let's see. So we are interested in describing the dynamics of a free particle under quadratic. I mean, I want to do it under quadratic approximation. So we will restrict ourselves to some specific sort of Gaussian wave packets, which on my observation I have seen that this can actually represent free particles pretty well. So we consider this sort of Gaussian amplitude function, and then uh, clearly then amplitude function is a Gaussian, and then corresponding to this Gaussian you get this value of the time, I mean, wave function at any time to be equal to this, which you have already established. And then let's just take a minute to talk about what is so special about this amplitude function and this wave function. So it turns out that this particular type of wave function, if placed within the I mean, if we place this with dispersion of free particle, that is h bar k square by 2m, then the dispersion relation, I mean, then it satisfies the Schrodinger equation. That wave function basically satisfies the Schrodinger equation for a free particle for any a and k naught I am considering there. Here, this a and k naught, as you can see, for any a and k naught, it will satisfy the Schrodinger equation for a free particle with this dispersion relation. So free particles then can be considered as some sort of Gaussian wave packets. That was my purpose, to consider this special amplitude function, and then the result onwards from here will completely be dedicated to the dynamics of a Gaussian wave packet in a force-free media, which will be associated with those free particles later. So now these are the results which I obtained under that quadratic approximation with that amplitude function. This is the wave function at any time t. This is, and where this theta term is basically this tan inverse 2h var t by m square, and m is basically the mass of the particle. And this, then if you do mod psi square, then you get something uh, this sort of expression you get for mod psi. This is basically the probability density. So see, typically this kind of situation happens. This animation, what it shows, that with time, as you can see, the Gaussian keeps expanding and expanding. Basically the width keeps expanding and expanding. Now let us see something called uncertainty relation, which this is basically what will uh, show that the width is basically changing under these approximations. So if we calculate the position uncertainty, which is del x comes out to be time dependent, and the time dependent um, del x is basically given by this expression. Delta xt is equals a by 2 square root of 1 plus this term, and then you get a momentum uncertainty delta p, which is basically time independent, which is quite expected because you have taken momentum as a constant of motion in case of a free particle, so it cannot vary with time. So the momentum space uncertain, the momentum uncertainty remains fixed, whereas the position uncertainty changes with time. So remarkably, as you can see, if you place t equals 0 in this expression of delta xt, then that, and if you place and multiply it with delta p, then it achieves the lowest limit provided by Heisenberg's uncertainty principle, that is h bar by 2. So this is basically known as the lowest energy wave packet. So, but as time passes, you can see that delta xt has some expression. With increasing time, the position space uncertainty increases, and hence the dispersion product del x del p also increases with time. Now, as you can see, this is the animation of time evolution of probability density function of the wave packet we have considered there for certain parameters. Now, this was something I was supposed to do, but I was unable to do. I wanted to animate the propagation in complex plane. So these are basically the real part and imaginary part of the position space wave function. And if one gives time as a parameter and then takes real part, imaginary part, and x as three axes, then one can see the movement of this or the propagation of this wave packet in complex plane, how basically it moves, but I was unable to do it. So now there is a question. I mean, what is going on? So whatever results we have got simply implies that the position of a wave packet just becomes more and more uncertain with time, whereas the uncertainty in momentum remains the same. I mean, this is kind of very counterintuitive from the perspective of classical mechanics. There you have, a constant velocity and constant momentum and everything, and you can precisely tell the position of the particle. Everything is possible, but here, as you can see, the uncertainty just blows up with time. So what's going on? So this, as I have written, that the Schrodinger equation with such fixed momentum particle results in a plane wave solution spread uniformly over the entire space. Hence, the solution cannot be normalized, hence there is no way to interpret it. On the other hand, from the quantum mechanical perspective, such a consequence was very much expected, as you can see, because we are making the momentum infinitely precise. You are giving a precise momentum to the particle, and then, of course, if you do so, then Heisenberg's uncertainty principle shows its play there, and you get absolutely no localization in position space. So the position space wave function just becomes uniform over the entire space. Now, then how do we expect this classical limit at all? Now, the thing is basically when we impose that the particle has high mass in proper scale, we obtain a very sharp probability density function whose rate of distortion is negligibly slow with time. So I'll show you some effects of, I mean, how this mass and this A, there was a parameter called A, how these two parameters affect this distortion thing. Because this distortion is the main problem. In classical world, we don't see that which times the location of a, I mean, the position of a classical particle is becoming uncertain. So let us see how can we encounter it. So now, why should the distortion be small at all, first of all? So in general, the expression for this time dependent delta x or uncertainty in x is given by this. I mean, if we ignore sometime, for some time, if we ignore this a term and this m term and take them to be in natural limits, that is 1, and just place the value of Planck's constant there, then t nearly comes out to be equal to order of 1 by h bar, which is basically 10 to the power of 34 second. So, which basically means that to see I mean, a order of one. I mean, a order of one change in delta x, you need 10 to the power of 34 seconds of time. I mean, even the universe, the age of universe is of the order of 10 to the power of 17 seconds, which is, I mean, then this time scale is very ridiculous, not achievable at all. So now if we talk on the order of that particular quantity A, what does it represent at all? So basically we have noticed that this uncertainty x was basically a by 2, and then a can also be written as h by delta p. So clearly a is involved with some sort of this width of position and momentum space wave function. So for the notion of classical particle, the position and momentum space wave function has to be well established, right? So what I'm going to do is I'm going to choose some specific a values for which I'm going to show that the localization is so strong that the corrections, or I mean the fluctuations in uncertainty is actually, I mean, it is not even observable. So a basically can take any value except 0, as you can see. So, and depending on the value of a, you will get position and momentum space uncertainties, of course. So let us see the limiting cases of these parameters. So if you take a tending to 0 situation, you achieve a very sharp localization in position space. That is, position of the wave packet becomes very certain. Then again, as a consequence of that Heisenberg uncertainty principle, when you Fourier transform it, then you see that the momentum has become infinitely uncertain. So that doesn't mean anything. And then for a tending to infinity situation, you achieve a very sharp localization in momentum space, but you lose the localization in position space. So that also can't produce the notion of a particle. So basically this, the second case, a tending to infinity, this is the situation we were facing back then when we were trying to simply solve the Schrodinger equation for a free particle. Because we have made the momentum infinitely precise, and as a result, we are losing the position space localization. So these are some conclusions that not all the solutions of Schrodinger equation for a free particle produces the notion of a particle. This quote unquote particle is basically I am associating with some sort of localization. One may say that no, there is no localization required for a particle, then yeah, of course that's true. But I am trying to retrieve the classical limit, so I need a localization there. Now, some solutions in fact doesn't have produce localization in either position or momentum space. Such solutions also exist, and some solutions are even not normalizable, which cannot be interpreted by the Born interpretation anyways. So, and yeah, that's what I wanted to say, that the quantum particle does not necessarily have any localization. Even a plane wave or rapidly fluctuating wave function in positional momentum space also can satisfy the Schrodinger equation for a particle in any kind of some kind of potential. Maybe it can happen that the solutions you get is not normalizable. So those are actually valid wave functions for them. But yeah, uh, you can regard them as a quantum mechanical particle, but in classical mechanics, you cannot associate a particle with such fluctuating, I mean, these sort of uncertainties. So, to have a desired localization, all I need to do is to choose that A parameter smartly, because it largely depends on the value of A. And now, basically, I discuss the effect of mass there. So as you can see, if you differentiate that thing, that position space, I mean the position uncertainty, with time, then you can see that there is mass term coming in the denominator. So which shows that if you increase the mass, then the rate of this distortion, this delta x, how this delta x changes with time is basically the rate of distortion. This rate of distortion basically decreases with time. I mean decreases with this increasing in mass. So I will, at the end of the talk, I will show you people some animations which I have made in using Mathematica, where I will show that, I mean, how basically these parameters affect the distortion rate. Now let us look at some, I mean, just a numerical example that, I mean, practical, let us take some practical situation that initially at t equal to 0, we have the appropriate notion of a classical particle. Let we have a very sharp localization in both position and momentum space. So initially you have that uncertainty relation, the minimum uncertainty relation, h bar by 2, the dispersion product. And then, I mean, the best way you can produce the idea of a sharp localization in both position and momentum is choose both this delta x and delta p of the order of 10 to the power minus 70. Because on the right hand side you have h bar, which is of 10 to the power minus 34 order. So it is best to choose around 10 to the power minus 17, and then it can produce a very sharp localization. So, and that localization will be established simultaneously in position and momentum space, of course. So, maybe if you are interested, then you can consider mass of 1 kg and then try to evaluate for 10 to the power minus 17 order of A, how much, I mean, delta x, how much it is coming out to be with time. And as you can see, the results I got is basically, even if you want an uncertainty of 1 meter, then basically you need 10 to the power of 17 second of order of time in order to achieve that much of uncertainty. So that is also now ridiculous. And then, I mean, if you even can measure something in in angstrom scale, if you are able to measure this length fluctuations, then it will still take you several years to detect any this sort of fluctuation there. Now, the small distortion, I mean, as you can see, the distortion rates are basically very small when we come to this classical regime where, I mean, this, there you have this specified this A parameters, there you have this very small distortions, and then the position space localization almost nearly remains intact. So this is somewhat equivalent to linear approximation case. That is, when you do quadratic approximation with this A parameter to be very small, then you get results nearer to that linear approximation case where there is nearly no distortion. I mean, in linear approximation, of course, there is no distortion at all. But here there is distortion, but the rate is very, very small. And uh, so now no distortion in position space. Let's just assume that the localized position space wave packet to be analog of a particle, because it is no more distorting like crazy as it was doing in the general solution. So this sharp localization in position space allows us to know almost precise position of the particle. I mean, see, if there is a uncertainty of 10 to the power minus 17 order, which is not measurable at all, then there is no point of, I mean, arguing that it's not a particle, because it indeed has a very sharp localization there. And then, as classical mechanics says that the free particle should travel with a zero or at least constant velocity, which you can clearly see because it is equivalent to nearly linear approximation. So you have this that group velocity concept again introduced here, d omega k dk at k equals k naught. That fixed with that fixed velocity, this wave packet will travel, which implies, of course, a fixed energy too. So there is indeed some sort of position and energy uncertainty there, but that's going beyond our realization if for those specific selection of parameters. So this actually seems to be the analog of the classical free particle which we see. So that was my idea on how to retrieve the concept of classical free particle using this quantum mechanical postulate. I mean quantum mechanical laws, of course. So now I want to introduce some sort of animations which I made. So first of all, as you can see, this was the change in, I mean, how probability density function of a Gaussian changes with time. The Gaussian wave packet, as you can see, the spread is increasing with time. Now let me show you some sort of, I mean, how mass affects these things. So this is another animation where I have kept this mass parameter to be 15, and this, of course, you should focus on the scale. The scale is small, I may make it large after some time, so you should focus on that. And as
Sorry, Krishanu.
yeah,
Uh, I think none of us can see your animation because you may have shared only the PowerPoint screen. Could you
uh,
please check that once?
oh, sure, sure, sure.
Animation is not visible actually.
uh, yeah, is it visible now?
Yes, now it's visible. Yeah.
So it is visible, right?
Uh-huh.
Yeah, yeah. So then I should continue from the very beginning. So yeah, this was basically the first animation I showed, that the probability density function of the Gaussian wave packet that I considered. That, I mean, basically that this was the wave function that I have got using that specific amplitude function. And if you set this kind of parameters, the parameters I have included here. So this you will get some this sort of animation that the as you can see, the width of the Gaussian is basically changing with time. That is, the position space uncertainty is also increasing with time. And now if I show you the effect of mass there, so this is basically mass parameter fixed to 15. As you can see, just focus on the rate of spreading. I mean, how it the speed of spread with time. And now, if I change it to uh, this, uh, so here the mass parameter is 100, and as you can see, the speed is decreasing. Yeah. So, and then if I increase it more, uh, maybe this one. This is mass parameter 1000. As you can see, this is basically, I mean, I have put h bar equals 1. So if I would have put h bar of the order of 10 to the power minus 34, then you can imagine, I mean, you couldn't have seen any change at all. It would have been just a line and which won't, I mean, the width won't be changing with time. This is how mass parameter affects it. And then you have this A parameter, as you can see. This is the animation corresponding to A parameter. So it basically reduces that amplitude of that wave packet as we expect there. So, and also it is associated with the group velocity. The velocity also increases as you increase this A, and the spread also increases. If I show you that here this A parameter is fixed to 10, and if I fix this A parameter to be equal to 50, then you can see that the spread is very, I mean, see, this is all very diminished, and then the spread has also increased. So this is the effects of those parameters. By only by choosing those parameters, uh, one can obtain such a sharp localization in both position and momentum space. So is my screen visible now of the PowerPoint?
Yes, yes, yes.
Yeah. So basically, then uh, in summary, I'll say that the
PowerPoint is
solution.
not visible. Your
Acha, I see, I see. So, okay, okay, wait. Yeah, is it visible?
So have you shared your screen? Because we can't see it actually, PowerPoint.
Yeah, I did share actually. Is it still not visible?
Just let me see.
No.
Okay, yeah. So sorry for the interruption. Our speaker is experiencing some technical glitches. He will just exit out of this meeting and come back.
Hmm.
Are people able to see the screen? It would be great if you just give your views. We sorry for the glitch, taking much time. We hope to return in 1 or 2 minutes.
It- Yeah, so
Fine,
only
fine now,
the
fine now.
summary part was left. I'll continue from there. So, in summary, I want to say that the solutions of the Schrodinger equation for a free particle, if you consider the free particle with fixed energy, doesn't produce any physically realizable solution because there is no localization in position space. And then theoretically, you can consider wave packets in quantum mechanics because they can produce such localizations at the desired point you want, and certain Gaussian amplitude functions along with the free particle dispersion relation, that is h bar k square by 2m, can correspond to such wave functions which satisfy Schrodinger equation for free particle and can establish the localizations of position and momentum space wave functions based on the chosen parameters A and the mass of the particle. So basically, the rate of distortion hugely depends on those parameters A and M. So depending, as you can see, that for an electron, that mass parameter is of order of 10 to the power of minus 31. So that is actually very small. So in that case, the uncertainty, I mean, as you can expect, that an electron in a force-free media, if you keep, then the position space uncertainty will become, I mean, become crazily huge with time. So, but in case of these classical particles, what happens is the mass and this basically the initial localization in position space uh, can show that basically it will take a huge amount of time to distort and to produce some sort of sufficient distortion to be observed, of course, and then we can beautifully retrieve the concept of classical free particle from there. So, of course, this has numerous flaws there, this work, because first of all, I want to say that, I mean, whatever classical particle you see around is not only a single quantum particle for which I have written the Schrodinger equation. It is a many body system, and establishing such position space localizations for such many body systems is extremely difficult. So uh, it it is not the, I mean, it is not that you can say from just this you can say that classical free particle actually corresponds to this very, Gaussian wave packet and this localization concept, because in reality localizing many body system is way more difficult than whatever they have done here. So I have just tried to produce some notion on how this localization is possible and how one can relate quantum free
No, we can't
particle.
see your slides. So could you please share them? Like, we can
Yeah,
see your slides for the. We can't see your slides. We can't see your slides. We can just hear you. And
uh, I don't get it. Can you repeat once?
actually, we can't see your slides actually. Could you
Oh,
please?
you can't see my
The
slide.
slides were not open actually. No, no, no. For some reason. Just wait a second. I'm coming.
Excellent.
Is it okay
So
now?
yeah, so that was, I mean, I just tried to, I mean, establish the notion of classical free particle actually, but it actually doesn't correspond to actual, I mean, form, I mean, the formalization you need actually to establish such many body localizations. So that's all from me. Thank you. And I want to acknowledge one of our PhD fellows, Vikramaditya Da, for helping me with several sorts of discussions and the mathematical issues I had during uh, this work. So thank you all. That's all from me.
Thank you, Krishanu. Thank you for the wonderful talk. It was really great to listen to your perspective. So, any questions or comments? The floor is open from anyone. So, I personally had a question. So, it's more of a comment actually. So, whenever you are like studying the Heisenberg uncertainty relation, okay. So, I guess you have used that here in your work as well, if I'm not wrong, at some point, in some form. Okay. So, the thing is that people, which include both physicists as well as mathematicians, are mostly familiar with the usual del x del p form of the Heisenberg relation. But what I want to emphasize is that it has some deep consequences in pure mathematics as well. Harmonic analysis, in particular, in the form of when you are using functionals over Lie groups, then it gives rise to some kinds of restriction in mathematics. You can understand what I mean. So over here, the picture of Gaussian wave packets and all those things come because you can't just treat one single quantum particle as a dot, of course, right? You can't. That's why. And you mentioned a very beautiful point in the end that even if you are trying to treat a huge body as many small quantum bodies, then also the approach mostly fails because it's a quantum many body problem, very difficult to solve. Okay. So that was my take. So I would like suggest the attendees to go through that. And if there, I will wait for 1 more minute for any questions from the audience. We apologize for the technical glitches in the between. So it was due to the internet connections in the Google Meet. Okay, so if there are no more questions, thank you so much. I would like to thank the speaker. Thanks to the people who attended. And this is, we are done with the 17th series of our seminar series. And we'll meet you soon in the next one. Thank you. Bye bye. Stay safe here.
Thank you.